So right now, I'm so excited. We are about to reveal new cosmology results that might or might not revolutionize the way we see the universe. In particular, data from DESI, the Dark Energy Spectroscopic Instrument, hinted that dark energy might not be the cosmological constant that many physicists assume it to be. And this has all kinds of implications for the origin and fate of the universe. But the statistical significance of these findings, which we broadcast last year, was not high enough to declare a discovery. But today I'm thrilled to have back Mustapha Ishak, Professor of Physics at the University of Texas, Dallas, and one of the leading scientists at DESI, to reveal their new results. We are about to find out if the status quo of the standard LCDM model is affirmed or if a radical rethink is needed to cosmology. So welcome, Mustapha. How are you doing?
Yes, thank you. Yeah, it has been very busy, but I'm doing very good. Very exciting times.
Yes, I just cannot wait to hear what the results are. But before we hear them, I thought maybe we should just set the scene a little bit. Why don't you tell us a little bit, what is a cosmological constant and how does it affect how the universe might evolve?
So the cosmological constant has been is the only term that we can put in the Einstein equations, and then we don't mess up, we don't touch the symmetries of the equations and so forth. So this term was introduced initially by Einstein in order to, for other reasons, in order to make the universe static and so forth. But then later on, much later on, the cosmological constant was brought back because it kind of allows the expansion of the universe to accelerate in its expansion. So it's like the cosmological constant in the equation of Einstein plays the role of some kind of repulsive force.
Right. And is it like a sort of constant, like a bit of energy for empty space? Can we think of it that way?
That is correct. Like you can view it as kind of, it could be a constant of nature, but I think if you put in quantum field theory into this, it's also viewed like the energy of the vacuum. So the more you have space, the more you have a cosmological constant.
Right. So what was discovered in 1998 that got this like the focus of the physics community?
So there was two teams working on trying to find to study the expansion of the universe, whether the expansion of the universe will slow down or will kind of is slowing down or is speeding up. And I think the common expectation was that the expansion of the universe was to maybe see slowing down because of or at least going at a constant rate, but it was not expected to see an acceleration of the universe. So in 1998, so there was two teams, one in Northeast, like I think John Hopkins, Harvard, and this Northeast, and in this Southwest, in the West, like in Berkeley, so there was another team working. So they were both looking at supernovae and how they recede from us. And then what they saw, each of them independently, is that the expansion of the universe is speeding up and not slowing down. And then in 2011 they got the Nobel Prize for that, for discovering that the expansion of the universe is rather accelerating and not decelerating or going at a constant rate.
So that seemed to confirm that there really is a cosmological constant. But there are alternative views. Could you just explain what the alternative views to it being a constant are?
Other possibilities are that in the universe there is a scalar field, and that scalar field has some kinetic energy, and that scalar field has also some potential energy, the combination of which gives you some dynamics. And this scalar field can have a thermodynamical equivalent property is called the equation of state. And this equation of state, like in the case of a cosmological constant, is equal to -1, exactly -1. But other possibilities can have an equation of state that is negative and close to -1. And again, like in the case of a cosmological constant, these solutions like quintessence, called quintessence scalar field, or for example, a modification to general relativity, the gravity theory, that can have an effective equation of state also close to -1. So it is not a mystery, it is not a problem for mathematics and for general relativity. If you take a fluid and you take that fluid and you put the you in that fluid you put the energy density, the pressure, and with a negative equation of state, then it gives you a cosmic acceleration. It gives you an accelerating expansion in the Friedmann equations. So, however, what is it exactly? That's the mystery. And as I said, so you have a quintessence field. You have a modification to gravity. There are other things like, for example, other theories of gravity, the way the matter is coupled to the space-time. It can also add additional terms in the Friedmann equations that could act like a cosmological constant. In fact, any modification to the equation of Einstein that could give you an extra term that look like cosmological constant can produce acceleration.
So one last question before we announce the results. Tell us a little bit about DESI. How are you able to distinguish between these different views of what dark energy really is? And how much data do you have now?
DESI was designed. It's an instrument that is put on the top of within the Mile telescope in Arizona, and it is able to take like 5,000 measurement of 5,000 galaxies at simultaneously. And it's also, DESI was designed to measure very precisely two things. It measures the distances to objects like galaxies, quasars, the distance, that one. Two, which is also very important, it measures the redshift to those galaxies. That means which is related to the speed, the velocity of this object. So you get an information for the positions and the speed, and it made the largest map of the universe, 3D map of the universe. So now we have 15 million objects, galaxies and quasars. Last year, when we did the first year, we had 6 million. And and then to the second part of your question is what DESI does by measuring these distances and measuring the redshifts. It's able to actually pin down to measure the equation of state of dark energy. In other words, this thing that we talked about. So a dark energy or cosmological constant, they have a pressure, they have an energy density. The ratio of these two, we call it the equation of state of dark energy. And it could be constant, as you said, and it could be constant. It could be a function of time. One thing very important here that is sometimes missed in the field is that only for a cosmological constant, this W, this equation of state, is equal to -1. And when it's equal to -1, it means two things. It means that the equation of state is constant, equal to -1. It also means that the energy density of dark energy is also constant in time. As soon as W is different from -1, regardless whether it changes in time or not, then the energy density of dark energy is dynamical, is evolving in time.
Last year, you had 1 year results and you had a hint of dark energy changing over time, which would really shake up cosmology. But the statistical significance wasn't quite high enough. But now I understand you have 3-year results. So what are the results? Do you see evidence of dark energy changing over time, or are we reaffirming the standard picture that dark energy is a cosmological constant?
The exciting answer is that now not only we see again hints for evolving dark energy in time, dynamical dark energy, but we will see it with a stronger statistical significance in this third year. So, two very important points to take into consideration. The first is that now the evidence, when we combine DESI data with CMB, cosmic microwave background radiation, and the supernova data, let's say we start with the DESI-5. When we combine these three, the evidence now is 4.2 sigma. What does it mean? It means that now it's 0.0002% that this result is a statistical fluke. In other words, it is such a small percentage that this could have happened just by chance. So this is very significant. So this is one. If we
Actually, let me
use
interrupt, Mustapha, because people would be familiar with the Higgs boson. When they announced that, they had to wait till they got to 5 sigma to say this is a discovery.
yes.
When I speak to astronomers, quite a few astronomers have said, and in astronomy, it's more like 4 sigma. What do you have to say about that? Is that about right? Or
I think if we take that metric, I think we are really above the 4 sigma. So this is very significant. This is, however, we want to be prudent as scientists, and we have the means to get to 5 sigma, and we are heading towards it. So why not?
yeah.
But I would like to bring. That's an excellent question, Phil. I have the second argument that I want to say, and I think I alluded to this, or I even said it last year when we talked, is that this is an important point. In addition to have a 4.2 sigma, we also, if we use other data sets, let's say we use the Union 3 supernova instead of the year 5, and then we get there, if memory is working here, we got a 3.7 sigma. A 3.7 sigma, so there is only 0.01%, not 1%, 0.01% that this happens just by chance or So, and now let's say we want to not include a given data set. We want if we take only DESI and we add to it the CMB, and that gives us again 3.1 sigma just by these two. If we combine DESI and the supernova DESI-5, it gives us 3.3 sigma. So here, and I mentioned this last year, when I saw this in December 12th, 2023, when we unblinded the data, I kind of saw that we are to something out of the ordinary. But as prudent scientists, we keep accumulating the evidence until we get to like the 5 sigma. But what I want to say is this. My own take, and I said this consistently for the last year and a half, is this. If I take a combination of data sets and it tells me a story, it tells me dynamical dark energy, and then if I start saying, okay, I don't like supernovae, some people don't. If I take away supernovae and I just use 2 other data sets like CMB and DESI, and they still give me 3.1 sigma, that is what? That is like only 0.05% that this is just by chance. If I see the evidence coming from different data sets independent, to me that is more important than anything else, in a sense that, all the different data sets, you have to start playing with the data and say, try to kind of find ways to run out of the results that the data is saying. So I think that to me, that is very important. Yeah.
All right. So what might this actually mean for the evolution of the cosmos? Because we've been told that we know it's going to end in a heat death. The universe is going to expand and expand at an accelerated rate. But is it possible, given this finding, that dark energy could even turn negative? And that's, in which case the universe would collapse, wouldn't it? Is this a possibility? I mean, how should we think of the evolution of the cosmos given this result?
Yeah, that is a question of interest. I don't know if we will be there to witness that, but yeah. I think as we see it now, is dark energy is weakening. Some papers have appeared to talk about the sign change and things like that. I don't think we see anything like that. What we see is rather that dark energy has been weakening over time. And if dark energy is weakening over time, that means, yes, eventually, if it continues, then the matter will become again dominating. However, now the question is, what is it going to change for the fate of the universe? So before, if it was just a cosmological constant or dark energy getting stronger, it will kind of make the universe expand very fast and get to a point where everything is isolated so far from the other ones and kind of almost an empty space universe again. However, what now come back to the table is that it's either the universe gonna keep just expanding at a constant rate, or possibly also not excluded that the universe could stop its expansion and recollapse.
Right. Okay, so there have been claims that the cosmological constant has this very unnatural value. So, for example, as I understand it, and correct me if I've got this wrong, you can calculate the energy of the vacuum, and when we measure it, we compare it to the value of the dark energy. It's out by, well, some people I've heard say 60 orders of magnitude, others 120. But if it's this, but I remember interviewing Alan Guth, and he said, but yes, this argument though assumes that dark energy is a cosmological constant. But there have been other suggestions, like in causal set theory, which is a quantum gravity theory. I think work done in asymptotic safety as well. And I know Alejandro Perez and his colleague Daniel Sudarsky, they work in loop quantum gravity. They've suggested, yes, it actually changes over time. So does this mean the value, we address this issue of the unnatural value for the cosmological constant? Or if it's not a constant anymore?
It's a good question. I think this question is that I think the finding that dark energy is changing in time speaks to the statement that it is not a cosmological constant. The cosmological constant associated with vacuum energy, and to me, what it is saying is that dark energy is not the cosmological constant. And in fact, here is the problem. You mentioned it. The problem with the cosmological constant is that the, say, quantum field theory approximation or calculations, if you take just the cutoff as the level of the electroweak theory or the QCD, so the first you get 40 orders of magnitude difference between what we are measuring from the cosmos and the calculation or estimations from quantum field theory. So I always found this is to be an indication that maybe this is not the vacuum energy at all. And this result to me goes in that direction, rather than starting now to take vacuum energy and playing with it to make it fit the observation. It didn't fit them from the very beginning. So now, does it resolve the problem of the cosmological constant, like our vacuum energy being this big? It at least puts cosmology out of that problem somehow.
So at the moment, actually, given the data that you have, W equals what?
Good question. So here is what it is. The exact values are as follows. So we have two parameters that quantify dark energy or modified gravity. Dark energy and the equation of state of dark energy. So there is W naught, that is the value today. And that one, instead of finding it -1 for like a cosmological constant, we find it that is bigger, something like negative 0.78, something like that. Okay? And then there is another parameter which is called WA, that is the slope, the slope of time variation. And that is one, instead of finding it equal to 0, we find it to be something that is actually negative, and something that is, if memory is working here, so it's something like way below 0, something like, in fact, between 0 and -1, closer to -1.
So in your opinion, if you had to guess, what are we seeing? What is the explanation for this changing dark energy?
That is a great question. And I have been thinking a lot about it. What we found now is two things. One is that it's not a cosmological constant. Two, it doesn't seem an obvious solution, a modification to gravity. Then what is it? It's still possible it's a modification to gravity, but not in the way we are we are approaching it. But what I think in here, we are in the same situation like 100 years ago, a century ago, when Einstein came up with special relativity. We have inconsistent things like observations seem not to agree within a lambda CDM. We see cracks in the model. So in my opinion, this could be a hint for that we are getting the entire picture wrong. And that's what I think we need to look into.
What about an effect of quantum gravity? Because there have been theories like causal set theory, I know very much predicts. Well, one, it predicted the dark energy, the 1998 results before they were discovered. And it did say, oh, but it would change over time. And there are other ideas in quantum gravity, asymptotic safety, and some kind of friction term. I was speaking to the loop quantum gravity guys. Could it be an effect of quantum gravity?
If it fits, if it first of all, it's completely consistent theoretically, and it makes its prediction. It doesn't adapt to the observation, but it does prediction. If that is the completely different picture of things, then possibly. That's what I say. It's completely something new in a sense that, but it could be something beyond that solution. But if that's a theory that predicts and fits the observation, be it. Maybe that's the big change. But my gut feeling is that it has been there for a while, quantum gravity as well, and there is a lot of work on it. We may be missing something even bigger.
So let's look to the future, because obviously this is a very radical result. So I presume other cosmologists are going to challenge it, as they should. How do we get further data? How can we cross-check this result? What are we going to find in the next few years that can say, yeah, this is the truth or not?
So last year in April at the APS meeting in Sacramento with my colleagues in DESI, and we presented the results there. So I remember when I was talking about that, I had goosebumps. But the tendency is important. And here we go, almost 1 year later, and we have more significance in the results. So although we need to be prudent, I think the tendency, where things are going, I expect this to continue. And although, again, at this point, it's very hard to say that we have to be prudent, we have to be cautious. But the expectation is that this tendency will continue, at least from my point of view. And then, as you said, yes, it has been challenged already. It's good to talk about that. It has been challenged in the sense, maybe you used a parameterization that gives you this. Well, now in this new result, we use like 5 parameterizations. We also used something that is not parameterizations. We did some binning methods. We did a reconstruction of the equation of state. And all the different methods, they indicate consistently the same thing. This is an important point. And what else? We also, and then other data sets. Other data sets are important, and as already in this present time, DESI, but also other data sets all point in this direction. Now, to validate this, we are very excited in DESI, with my colleagues in DESI team, we are all very excited because we will have the year 5 data. Okay, and that's, yes. So we will have 50 million galaxies and quasars to redo the same analysis. And 50 million galaxies, we are expecting the significance to go to as high as 4.9 sigma. And then there are other experiments as well, like LSST DESC. Let's see what Euclid, let's see a Roman telescope. So all of these ones will give us other constraints on what dark energy is. And so it will tell us, confirm this result and or have more evidence to it.
So thank you, Mustapha. This is so exciting. I hope you'll come back when you've got the 5-year results and we'll see what happens then.
You're very welcome. These are very exciting times and I'm looking forward to it as well.
All right. And if you have any comments, please leave them in the comments. If you like this content, please like and subscribe. And we'll see you next time. We have some exciting news in cosmology.